Good afternoon and welcome back to CS240. This is Intro to Computer Systems, and we are going to dive in exactly where we started off. So we have been talking about the CPU, and this is the second data foundation, or second foundation of a computer system, and we're going to finish up the CPU today. Because what I want to give you is I want to give you enough understanding that you know it's not magic anymore. That you know that the CPU doesn't just magically do something, but you have an understanding of how we actually build the CPU with actual hardware and how instructions are actually ran on that CPU. So the first instruction, the only real instruction we're going to dive into, is the idea of how do we do an addition, the add instruction, on a CPU. And we left yesterday, or Tuesday, with the idea that we built a half adder. A half adder was a thing that we could take inputs A and B, and we added them together, and we got a sum output and a carry output. So we got these two different outputs from the half adder. And then we said we want to build a full adder. And the last thing we did on Tuesday was to actually build this full adder, which is to add 3 bits together and produce an output bit. So the idea is we have now not just A and B, but we have A, B, and a carry in. So an input from like the previous bit operation. And then we figured out what the output would be. We have this idea of a sum bit and a carry bit when we add 3 numbers together. So what we said was we wanted to figure out, can we build this with just half adders? What do we need to do if we want to build this with just a half adder operation? So what I think would be really useful is let's go ahead and just throw A and B through a half adder, because that's essentially what we did to get sum. The sum is just A plus B plus C. So I think it actually would be very interesting to put in a half adder with the inputs A and B. So I'm putting inputs A and B into my half adder. And we know that the output from the half adder is going to have a sum bit and a carry bit. So I'm going to write here sum and carry. And here I'm going to say, okay, if I'm just adding A and B together, I can compute what is the truth value for A and B when I have the sum bit and the carry bit. So the sum of just A and B, 0 and 0 is 0, 0 and 1 is 1, 1 and 0 is 1, 1 and 1 is 0 with a 1 carry. And the first 4 bits, or the first 4 rows, are the same as the last 4 rows, because the only thing that changes is carry in. So we know that that's also then 0, 1, 1, 0. So I have one half adder that is able to do this. And then so I left this as a challenge. Give me an idea of what I should do with the second half adder. What should the inputs of the second half adder be? What should I try out? There's a lot of different solutions to this, so the thoughts. Inputs into the second. Guys, are you really leaving me hanging? Okay, yes.
You just sum both of them?
What do you mean by sum both of them?
The SNC or the inputs to the half adder?
Oh, so I can sum the sum and the carry from the first half adder into the second half adder? Maybe? Okay. Did you work out something? Did that work for you? No. Guys. No one? Yeah.
Can you have the sum from the half adder with the original key in?
Oh, so the sum from the first half adder into the carry in. Did you try it out and get something?
Yeah.
Yay! Guys, I'm otherwise disappointed. This is really sad. Nothing at all. One person. We can do better than this. This makes me sad. But let's see what happens if we go ahead and follow. Remind me of your name. Aaron? Aaron's idea. So let's see if we have a carry input, and let's say that the carry input's one input into our second half adder, and the sum bit from the first half adder, I'm going to call this half adder 1, the half adder 1 sum bit. So I'm going to use the half adder 1 sum bit and the carry bit and put them both in to this second half adder. And then let's see what the sum and the carry out of this second half adder is when we do this particular design. So sum bit, carry bit. So the sum when we have carry in, So I'm looking at carry in, and I'm looking at the sum of the half adder 1. So these two bits are right next to each other, so this is great. So 0 and 0 is 0, 0 and 1 is 1, 0 and 1 is 1, 0 and 0 is 0, 1 and 0 is 1, 1 and 1 is 0 with a 1 carry, 1 and 1 is 0 with a 1 carry, and 1, 0. So then everything else is a 0. So what I've done is I have now set up two half adders that I think is going to help us get the result of the sum and the carry in that we have at the very end. So I'm going to look at the sum, and I'm going to look at the sum column and see that this is 0. And I'm going to notice that this is 0 and this is 0. So if I just look at the sums and the sums, I notice that all of them are zeros. That seems great. 1 and 1 is a 1. 1 and 1 is a 1. 0 and 0 is a 0. 0 and 1 is a 1. 1 and 0 is a 0. 1 and 0 is a 0. And 0 and 1 is a 1. So is there any combination of these three columns that looks like something we've seen before? This is a gate that we recognize. Specifically, when sum of the half adder 1 and sum of the half adder 2 are both zeros, what's the output? 0. And if either one of them is a 1, what's the output? 1. So what gate is this? OR, yeah. Oh, okay, yeah. So this doesn't actually work here, right?
The sum actually matches the S1 right.
The sum what?
The sum actually matches the S1, like the second S.
The sum actually matches the second S. Ah, okay, yeah. So we found out that this OR relationship doesn't actually work. We found an error here. So we don't just sum those two together, but instead, Erin noticed that in her solution, actually, is this column and this column the same? Yeah, they're identical. Ooh, this is a clever solution. I like this solution. So in this clever solution, I'm going to start drawing the full circuit diagram. So we have A and B coming into a half adder, and then we have carry in also coming into a half adder with the sum coming out of the first half adder. And we found that this output, the sum out of the half adder, is exactly the sum of the full adder. We don't even need to do anything else. This is fantastic. We drew a really simple circuit that when we sum three things together, we have two half adders we can build together, and then we get a sum byte out at the very end. So we've done 90% of the work. Now the only last thing, sorry, this green shows up terribly on the monitors. I won't use it again. The last thing we need to do is figure out how do we get this carry out bit. So now we need this carry out. 001, 0001, 0, yeah. What are your thoughts?
Could you do OR with those carry bits for the half adders?
Can I OR the two half, so can I OR carry 1? So you're saying I'm going to OR this column and OR this column. So let's test this and see if this hypothesis is true. So if I OR 0 is 0, that looks good. 0, 0 is good. 0, 0 is good. 1, 0 is good. 0, 0 is 0. 0, 1 is good. 0, 1 is good. 1, 0 is good. That looks fantastic. So remind me of your name. Varun said, I can just OR carry out of the first half adder and carry out of the second half adder. So let's go ahead and do this, and build an OR gate. And we have a half adder. Is this your solution?
Why XOR?
Oh, did I put XOR? I completely did write an XOR. Thank you. Yeah, XOR would have been wrong, I think. Oh, XOR would have worked as well. Yeah, I think I've seen it as XOR in some of the, so a different solution. When you draw some of these differently, I think you require an XOR. Clearly, XOR also works here, but I think OR is generally a simpler gate. It's probably cheaper to manufacture. So you just saved our company millions of dollars. Thank you. So yeah, we've got an OR gate instead of needing an XOR gate. But it could have been an XOR gate. The truth table works out still. All right. Any questions on this? Now, the best thing about being a computer architect, do we ever want to do this again? No. So what we can do is we can say this entire thing is now a full adder. So a full adder has 3 inputs, A, B, and C, and then a sum and a carry output. And we never have to think about what the full adder is actually doing anymore. So we've just abstracted ourselves another level higher. So we can now think about how we actually build something with a full adder. So here is another diagram of a full adder circuit with just gates. So I put some half adders. We abstracted away. Half adder, this is basically one of our half adders. This is another half adder. And then here is our OR gate that we did. So here is the exact same diagram that we just developed together in full circuits without needing to abstract them into half adders. But you can see we can reduce the complexity by using components that we've already built. So I want to do one final thing to just make sure we can actually do addition. Because everything we've done so far, A, B, and C are a single bit. But we don't just work with single bits. We want to work with bytes and bigger objects. So what we're going to see is there is something that allows us to take in an entire input, and we're going to represent the input now as A being a 8-byte, or say an 8-bit number, which I'm going to represent as A0, A1, A2, all the way up to A7. So the idea here is now A is actually 8 bits long. It's an entire byte. So these themselves are your zeros and ones. I'm going to do the same thing with B and the same thing with C. So when I say A0, it's just the 0th bit in the number A. So nothing scary here. And I'm going to go ahead and build a ripple carry adder. So we're going to chain circuits together, and this builds a ripple carry adder, or an RCA. And the ripple carry adder, what it's going to do is it's going to go ahead and carry that input, or carry the output of my full adder, that's the carry bit, and carry it into the input of the next full adder. So what this means is I have 2 numbers I want to sum together. I have number A0 and B0. I'm going to put these into my full adder, and I'm going to get some output, S0, the sum of the 0th bit, and I have an output of the carry that I want to go ahead and put in to the input of my next full adder. So then A1, B1, this is the full adder. It adds what the first bit is. The carry follows over to the next one, and we're sort of rippling this through A2, B2, sum together, the output becomes S2, this carry goes over. Then finally we have an A7, B7, this outputs S7, and then we have a carry out, which ends up being our overflow in an unsigned notation. So we're rippling this carry along, and this is a simple way of adding two numbers together in a bitwise fashion, so we end up getting the sum of those two numbers out on a circuit. And this is called a ripple carry adder, or an RCA. And this is the simplest adder you can build in a computer system from a design point of view. But do we like this adder? What are problems we see? Do any of you guys see things that we don't like about this design? Room.
It gets there's a lot of more circuits whenever you
Okay, so yeah, this is lots of gates. So each of these full adders are like 5 gates apiece minimum. So now we have 5 if we have a whole bunch of bytes, or sorry, a whole bunch of bits, 64-bit system, 5 times 64, over 300 individual circuits and a whole bunch of wires, just to do an add operation. And do you think the same thing, or?
We have to wait for the carry, and like,
Ooh.
the longer the numbers are, like, the longer it takes for the carry to ripple through.
Yes. Oh, so this is brilliant. When we have to calculate a number, we have to calculate A0 to get the carry from A0, to get basically the carry 0, before we can calculate the A1 plus B1, right? We have to wait around for that carry bit. So if we assume that this circuit runs in every single clock cycle, if we have a 64-bit machine that's adding 64-bit numbers, that's 64 clock cycles before we get our result out, right? Because we don't know what the carry in to the 63rd, we don't know what C in 63 is until we finished the full adder for 62. So this has a whole lot of gates. This is slow. It has this dependency effect. We're dependent on our previous result before we can get our next result. So that's a couple disadvantages. Anything else? Yeah. Remember your name again? I say what? Dylan. So Dylan said it only works up to 8 bits. So could I add actually more gates on the end?
Yeah.
Yeah, so I think I can fix that problem.
Then it becomes like less efficient for children per
Oh yeah, so I can say slow. I can add, Dylan sort of is even more specific, and even more slow with more bits. So graphics cards are usually, modern graphics cards, like the top-end graphic cards, I think are in the 300-bit operations now. Because what graphics cards basically do is they parallel a whole bunch of operations, so they do the same thing to a number of bits. So you have these words that are just extremely long. So if you're adding something on a graphics card that is a 300-bit processor, then you're going to have 300 of these gates. So it gets even slower and slower in a graphics card. So the more bits you get, the slower it gets. There's this linear increase between speed and the number of bits. So these are some really good disadvantages of the system. Any other thoughts on this RCA? Yeah?
I'm not sure if this is a disadvantage, but because we have a bunch of summed outputs, wouldn't it take a bit to concatenate them?
Oh, because we have a bunch of summed outputs, does this take a bit to concatenate it into a big number? Given that they're all going to S0, S1, S2, that's going to be fine in hardware. There's no concatenation that's needed, just go into the right spot. Yeah? Do negative numbers really work with this? So the beauty of it is we're going to use 2's complement for negative numbers. And because we're using 2's complement, we can just use regular adding. So negative numbers are totally fine. The only thing that's not in the circuit that would be easy to add is overflow detection. So we could have an overflow circuit that basically checks if A7 and B7 are the same and S7 is different, then we set the overflow bit. So yeah, the negative numbers are going to be okay here. Yeah, costs, lots of gates, yeah. So definitely expensive. Lots of gates, and that implies really expensive. And we want to make our circuit as cheap as possible. So these are just some of the disadvantages. And you can go into an architecture course. I actually don't even think you optimize this too much in 233. It's really the ECE courses that look into how do you optimize a circuit. Something like addition has been optimized just insanely. You can look up a bunch of stuff on SIA, how to make a really efficient addition operator or addition circuit. So we're not going to dive into the optimization of this circuit. There are things that people do. Addition's very fast in a computer nowadays. But this is the basic idea. What we took was we took the idea that we have lines that have power. So you have electricity flowing through these lines that are labeled A0, A1, A2. And when we want a 0 represented in the computer, we have no electricity there. If we have 1, we have electricity. We go through a series of transistors, which we represent as gates, which allows us to do things in the computer like add numbers together, as long as we have rules on how we represent binary numbers. So the goal here is to really give you an understanding of how the actual computer works at a deep level. Where if you wanted to learn more, now you know where to look out to learn more. I want to just mention one last thing before we finish up lecture 3. And that is how when you work with computer architects, they use a different mathematical notation for a circuit than we have generally talked about. So when I use notation, I generally fall back on notation you're going to become very familiar with. This is the 173 notation for binary logic. Computer architects decide to use different symbols. So when we work on looking at truth tables, I'm going to use the symbols that computer architects use. So the symbols that computer architects use is we're going to have, when we want an AND gate, they just use a times sign or nothing at all. So if you have inputs A or B, it can be A, B, or A times B. This is going to be the format that you're going to see architects use. They usually don't even use the times sign. They just go ahead and put them right together. If you have an OR gate, they use a plus symbol. So that's going to be A plus B. And if you have a NOT, they use a single quote. So if you want not A. So exactly the same that you are familiar with, just slightly different notation. And there's one homework question I have for you that I do want you to kind of think about what we just thought about as the challenge between lectures of how do you design a circuit and a truth table. So I have a few simple ones for you where we'll go ahead and use this notation that's used by computer architects. Any questions on circuits, or do we want to just be done with these guys? Are we done with them? Yeah. An XOR. I mean, I'm guessing it's, I'm actually not sure. I don't do much computer architecture. I'm guessing it's going to be your classic XOR symbol that you see a lot, but I'm not actually 100% sure. We won't be using XOR. It's a good question. Cool. All right, then let's finish. Let's say goodbye to our CPU and begin to transition over to how does a program actually work. So if you don't have handout number 4, I've got handout number 4 up here. And Aaron, yeah? Are there other components of the CPU you should know about? We're going to now start talking. We'll talk about a number of kind of what's on the CPU at a logical level. So we're not going to talk about the hardware of the CPU anymore in the sense of how do wires get drawn. We're going to talk about like how is data stored on the CPU? How do we process data on the CPU? So we won't ever see a wire or a circuit diagram again. Instead, we're going to go a level higher up and basically be, as programmers, how do our programs actually get ran on the CPU? How do we tell the CPU to add 2 variables together? So that's going to be the progression that we're going to go. So I'm going to move over to the next set, just to kind of keep things just parallel with the handouts. And this is, so I feel like the beginning of this course is really all about sort of just giving you an idea of how the foundations work. But now we're getting closer and closer to my favorite area. This is the area of systems as a whole. How do we actually build things and build software up? So one thing I asked you on the very first day of class is to figure out what ISA your dream computer had. And we talked on Tuesday how a lot of you loved some Intel or AMD chips. And this Intel or AMD instruction set architecture is going to be one of the two common architectures out there. And Intel or AMD, you guys learned that this architecture is called an x86-64 architecture is the full name for it. Sometimes you see it just written as x86 or x64. But all of these terms in modern times are pretty much synonymous. It's a 64-bit variant of the x86 chip. And this is the first type of instruction set architecture that's extremely common. The other type is going to be the chips that are made from Apple, Qualcomm, Samsung. So basically, chips are in mobile devices, and a few laptops are an architecture called ARM. So this is sometimes seen as ARM v8 or A64. So pretty much all of the chips that are manufactured today, with very few exceptions, are either going to be an x86-64 chip or it's going to be an ARMS chip. And in general, if it's a low-powered device, it's probably going to be an ARM chip. If it's a high-powered device, it's probably going to be an x86 chip. And these two are completely different in many, many different ways. These are two different ways that we can actually give instructions to a computer. And what we can do is we can understand what do these instruction sets give us. And one of the things that instruction set architectures give us is it gives us how much data we can actually use inside of the CPU. So every single CPU, it doesn't matter if you're an ARM chip or an x86 chip, every CPU has a limited number of these things called registers that are used for general purpose CPU operations. And pretty much everything has to be inside of the register. So with very few exceptions, all CPU operations happen on data in registers. So this is the idea that we're going to wire up a CPU to just a limited number of registers, so we don't have to spend too many wires wiring all of those, that A0, A1, A2, A3, all those wires that went from A that had electricity on it, that went into our CPU. Well, we're going to have a very limited bank of where those wires need to be. So the registers are actually hardwired to all of our CPU components. So we're going to have to put data into our registries to actually do math on them or do any CPU operation on them. So this is the CPU registers, and these operations that we're going to do, the instruction set architecture, the ISA defines all of the possible operations we can do on an actual system. So there's going to be logical operations that, like and or. There's going to be arithmetic integer operations like add, subtract, multiply. We have the floating point versions of them. We have things like jumping to other random pieces of code. We can call functions. We can move memory around. We can exchange the position of memory. We can push or pop onto a stack inside the CPU. These are basically your operations you're going to see on any instruction set architecture. And what I want to give you today, the biggest thing, is the idea of how in the world does the code that you write and everything that you've been doing since you've started doing computer science actually get translated into this, so the CPU can actually run the add operation that you saw how the circuitry worked. And to do that, I feel like it's best to actually look at some code. And sorry, I forgot one thing, just to mention this before we look at code. ARM processors, we talked about ARM processors being lower power devices. So ARM processors have a significantly fewer, smaller set of instructions, and they are known as reduced instruction set computers, or RISC. So the idea is they're just going to have a few instructions, pretty much the instructions that were listed above on your handout. That's pretty much the set of all of the instructions on a simple RISC computer. You don't really need much more than that to do most everything you need to do on a computer. On the other hand, x64 processors have a much greater set of instructions. They have a lot of really specialized instructions that can do really detailed calculations. And they're known as complex instruction set computers. Or CISC. So ARM devices are reduced instruction set. x86 devices are going to be complex instruction sets. The big difference is, so for a RISC device, you need less actual hardware because there's fewer instructions. So RISC is going to be less hardware. More optimized. So you can really optimize those few 50 instructions that you have on a RISC architecture. You can really optimize that circuitry, optimize the design of the chip. But for a complex instruction set, you have more hardware, but you have special opcodes to do complex tasks. So you might want to calculate a cryptographic hash. There may be an algorithm that does a cryptographic hash. So on complex instruction set, you have a SHA-256 instruction. So this is a hash that is a cryptographic hash that takes in data and produces a summary number of that data. That's an instruction that exists in complex instruction sets. And they've built the hardware to do all of that instruction very, very quickly. In a reduced instruction set, you've got to run all the individual operations as part of that. So generally, RISC reduced instruction sets like ARM processors are lower power. Generally, complex instruction sets like Intel's are higher power. So there's sort of a trade-off. It seems that we're trending towards these reduced instruction sets. That's what Apple Silicon did. That's what every cell phone has done. And it's kind of the way systems have been going. But what, yeah.
So is this because computers are getting smaller?
Is it because computers are getting smaller? That's a good question. I'm going to guess that not just smaller, but needs to be last longer with a battery. I'm going to guess it's power more than anything. That I think that we're prioritizing lower power consumption and longer battery life over being able to do the fastest possible processing. But that's more speculation than anything. That's a great question. Yeah, I'm not sure why the global trends are going a certain way. But these are kind of the two different competing camps. Because certainly 10 years ago, I would have said RISC processors are almost dead. Almost no one's using RISC processors. And it's really the cell phone that's brought RISC processors to the forefront. So let's actually look at code. I want us to start seeing things as a computer scientist. Because we want to know how our code we write actually runs. And I want you to be able to have an understanding of how you can dig into a program and really understand it at a really, really deep foundational level. So what I have is I have a very, very, very simple program. So this program is a whole bunch of int operations. Set an integer 0, add but 3, subtract 2, multiply by 4, divide by 2, multiply by 5, print something out, and multiply by 479. So we could figure out what the value of this would be, but I want to just go ahead and compile this code and then run hex dump of the output. So I'm going to do exactly this. So I'm going to run these two commands so you know I'm not lying to you. So here's o4.c. It's the exact same program you saw here. I'm going to gcc o4.c. It compiled, and then when you compile something without any output, it gives you a program called a.out. So I'm now going to object dump, not hex dump, minus d of a.out. And what this gives us is it gives us the actual executable code that your CPU is going to run. So if I scroll up, I should get to a main right here. So here is the main function. And what we'll see is I have taken all of these instructions and transcoded this output that I got right here onto your handout so we don't have to reference back and forth. But what you'll see is this should match exactly, that the first operation is an F3 operation, F3, then a 55, that's great. Then we have a move L, perfect. So this is a perfect match. This is the exact object dump of this program. So I just took C code that you know how to write, compiled that C code, dumped out the object file that was created. And now, I want to go through and actually see what's going on. So the first thing, int main. What's happening is we've got this first command that basically says in break 64. And we know that this is the name of the command that the processor's running in hardware. And it's defined by the first hexadecimal byte. So I'm going to actually skip the first one. Int main is kind of uninteresting. So if I go down to the fourth line, I'm going to say, here is int a equals 0. And we see this C7, this is called the opcode. And this is the operation that the CPU should run. So which circuit should I move this data to? And this particular opcode corresponds to move L. So I compiled it on this computer. This is an Intel computer. So what I can do is if I were to open up Chrome, I can say opcode x86 move L C7. And I should see that I have the x86 reference set, and we can see that, hey, here's a move operation, and C7 is the opcode, and we have the technical specification of what the actual CPU is going to do with this operation. So what we have is we have the C7 opcode. This tells I want to move data, and this particularly says I want to move the number 0 into the register called RBP. So this is putting 0 into one of my CPU registers. This register's name happens to be RBP. And this is what the hardware is actually fundamentally doing. Then A equals A plus 3. Well, we said inside the CPU there's an add circuit, and we've asked the CPU, opcode 83, to add, and I'm adding 3 to the register RBP. So that had 0 in it, and I'm adding 3 to 0. That gets us 3, right? So that makes a lot of sense. Very next line of code, A equals A minus 2. Well, subtracting, which is the opcode 83 as well, 2 register RBP. Yeah?
So the output tells us both the operation and the register, or just the...
So the opcode only tells us the operation. The register, I think, is the 3rd byte. Because, yeah, you see FC here as well. So all of these, because they're all working on the RBP register, you're seeing that same you're seeing that same FC. Does that make sense? Yeah, that's telling us what register we want to work on. Yeah.
So, like the left side, like the numbers and the letters and stuff, that's like hexadecimal representation of machine code, is it not?
Yeah, the C7. Yeah, this is the actual hexadecimal representation of the executable file. If you were to go and open that up, you would find these exact bytes in this exact order inside the executable file.
And then on the right-hand side, like the move-all, that's like the assembly code.
Yeah, the move-all, well, it's the human readable representation of that exact bytes. So basically, as a human, if you wanted to write assembly code, you would write the right-hand side. The left-hand side is how the computer represents the right-hand side. So basically, these bytes turn into this assembly code. We don't compile between the two of these. Basically, the 83 is just how we tell the CPU that we want to do a subtract operation. Does that make sense? Yeah, so this is actually, we don't actually compile between the left and the right side of these numbers. This is actually the representation of what's happening in the CPU. Yeah? What distinguishes add and subtract? I am pretty certain that it's a 2-byte operation. So basically, these second bytes actually tell us more about whether or not you want to do the add or the subtract. You would have to reference actual technical documentation to kind of see. I don't know x86. x86 is a confusing architecture. If you took 233, you would spend about, there's a few people who took 233 in here, right? Yeah. So how long do you spend doing MIPS in 233? A few weeks? Yeah, so in 233, you would spend a few weeks actually programming a language somewhat similar to this, but way more simple, right? Called MIPS. So x86 is kind of a complicated instruction set because it does a whole bunch of different things. MIPS is a super simple instruction set. But if we're going to get to cloud programming, I don't think you really need to be writing these lines of code. So you can just write C code and have a compiler do that for you. So subtract L subtracts 2. Line 7, SHL. Well, that's not what I expected. I thought I was going to see multiply. Any idea what SHL might be doing? Shift? Shift where? Yeah, shift left. So when I compile this code, A equals A times 4, it didn't actually multiply by 4. It said, hey, I am going to shift left by 2. And that's exactly what we said the computer was going to do when we talked about multiplication on Tuesday. It's going to just shift our bits. Oh, clever. Okay, A equals A divided by 2. What do we expect A equals A divided by 2 to do? We expect it to shift right. And how far? 1, right? 2 to the first power, so just shift left of 1. But what actually happens? Ooh, 1 line of C code just turned into 6 lines of assembly. What in the world might be going on here? So on this first line of assembly, we moved our data in from A into a new register called EAX. So now EAX contains the same value of A. Then we moved it again into EDX. Not sure why we're moving. I don't know why it moved twice. And then we shifted right by hex 1F. So what is 1F in decimal? 31, yeah. So it's 16 plus 15. So it shifted right by 31. Shift right by 31. What in the world does a right shift of 31 do? Why would we do this? Oh, this is really interesting. So what happens is an integer inside of C is 4 bytes long. So it's 32 bits long. So if we have this integer, 0, 0, 0, 0, so the 31st bit is the most significant bit, and we said the most significant bit in 2's complements, which is what we're using to represent, that is the sign bit, right? So what it did was it grabbed the sign bit into EDX. So EDX now just contains 0 if it's a positive number and 1 if it's a negative number. So it got rid of all of the other bits by shifting them away, and we just have the sign bit remaining. And then it added EDX, or EDX was added to EAX. So we added the sign bit to the number. So basically, to divide a 2's complement number, we actually have to first add a 1 if it's a negative number. And if it's a positive number, we want to add nothing. So what it did was it just grabbed the sign bit, and the sign bit is now stored inside a register, and it adds that sign bit to the number, and then it shifts the number right by 1. So this is what a computer did when we're asking it to divide by 2. And this works no matter if it's a positive number or a negative number. So this is clever. This is interesting. This you can really get into the code. And then it moves this back into our original register. So EBP is where the variable A is being stored in our program. Yeah?
Why is the opcode between the two operations different? Is it because you're going from opcode to a register versus
This 8B and 8.9?
Yeah.
So the thing I kind of simplified is registers that start with R are 64-bit registers. Registers that start with E are 32-bit registers. So I'm guessing it's because one is a 64 to 32-bit transition and one's a 32 to 32-bit transition. So that's why you're seeing different opcodes for the same operation. So yeah, I basically it moved our 60, I'm actually not sure why it stored an integer, our 4-byte integer, in a 64-bit register. That's an anomaly. I think if you might have used some optimization like -O when you compiled it, you might have seen it not do this. This is unoptimized code. Yeah. So in x86, the opcode is variable. Some opcodes say you're going to use the second bit, or second byte, to determine what the opcode is going to do. Some of them only use 1. Yeah, x86 gets complicated. It's disgusting. All right, so I want to just go through a couple more of these and just give you the idea that everything you see, or sorry, yeah, did you have a question?
Yeah, I just had a question. How come, like,
How come that multiplication and subtractions don't need the move statements? So I'm guessing that the R register, the RBP, is a 64-bit register. So for some of these things, when we're shifting around, we need to make sure that we're only shifting around 32 bits, because the integer is only 32 bits. I'm guessing it has to do with that. I'm not actually sure why the compiler chose to do this. If I wrote this by hand, I would not ever use I would never use the RBP register. I would just use like the EAX register if I was writing it by hand. But if you're writing assembly by hand, you've just written a 50-line program to do literally simple math. So certainly, can you optimize a program by this tiny fraction if you do it by hand? Absolutely. Is it worth your time as a computer scientist? Please never do it. Oh my gosh, that would be so painful. So yeah, definitely compilers are really good. And this is without optimization turned on. If you use a -O inside of -O like 3, that turns on like high-level optimization when you compile it. So that would speed it up. That would probably make more efficient code. Yeah.
If it's an optimization, like the compiler just like not bothered to like add emphasis to optimization.
That, I would hope that the compiler would be smart enough to realize that it just have a static number at the end. It'd be interesting. We could try it out for sure. I might do that afterwards. Yeah.
I think that would work for like a lazy evaluation system where like it wouldn't even go into the compiler if it doesn't like know that it's like because I know that some movie uses evaluation.
Yeah, so the question is, can I because basically the A is always going to be the same at line 12, right? That A is always going to have a fixed value because A is not actually dependent on input. So the question is could the compiler be smart enough to realize under optimizations that you don't need to do any of this calculation? And that's something that I'm going to check after lecture. I'm going to try and compile it with optimization code and see what the assembly looks like. So I think that's a really interesting question. So we've seen division. I want to look at a couple more. So A equals A times 5 is the next line. And A equals A times 5. What do we expect? So when we talked about multiplication, we said that computers often don't just do multiplication. Instead, it's going to do shifts when it's possible, right? And what do we see here? We see a shift left by 2. So we see A is shifted left by 2, A is shifted left by 2, and then A adds, EDX is added to A. What is EDX? Well, EDX, what was the value before shifted? So it basically took that original value of A, stored it, shifted the values by 2, or shifted by 2 bits, then added that original value. So we basically have 4 plus 1, 5. So it's smart. It knows to use shift operations and add operations to do multiplication. It's exactly what we learned about on Tuesday. It exactly is what the computer does and when we actually run the program. And then printf, so there's also commands to call out to other programs. So printf is something that's defined in the standard library. So you see that this loads in the string. So this string is located in my program at location 2004 or hex df0. That is the pointer to basically the string high inside of my program source code. It's going to load that in. It's going to say that's the last argument. It's going to go ahead and call printf. So now it's going to call off another program or a function to actually do the printing f. So it works exactly the same as you might expect. The last thing is I was wondering, can I finally get the multiplication operation to be used? So I was like, what's a disgusting thing to multiply? And I was like, okay, what if I did something like 256 plus 128 plus 64 plus 31, something that's basically going to be just disgusting to actually multiply out by doing shift operations. And you'll see that when it becomes really disgusting, the compiler said, you know what, this is disgusting. So I'm just going to say, I'm going to multiply my RBP, which is actually stored in EDX, by 1DF. 1DF hex is 479 in decimal. So we see that in this case, it just went ahead and used the multiplication operation. So the reason I wanted to go through this with you is to show you that everything you see when you program up just goes down to assembly, gets compiled into this object bytecode, and then your computer has operations defined by the instruction set architecture that is going to run this code. If you have an M1 computer, your instructions that you're going to be compiled to is going to be completely different as far as opcodes go. They're largely the same named instructions. Generally, add is still add. But the opcodes are going to look different because these are opcodes for an x86 system. ARM opcodes are different sets of numbers. Yeah?
Instead of A equals 8 times 5, instead of A equals 5 times 8, is that the same code?
You can try it yourself. I actually don't know. I'm going to guess yes. But you can take this program, run these exact commands, and you'll be able to get the same output. And that's what I'm going to really try and do in this class for the entire semester, is I don't want you to have to believe me on anything. I want to make sure I've enabled you to actually do all this yourself. So you can nerd out with this if you want to. So there's two last final bits I want to talk about, or two last things. The first is the program counter. So how does your program actually run? Your program counter is a special purpose register. So this is a special purpose register that points to the current opcode. So literally what happens inside your computer to get your program running is the program counter is going to be set equal to the memory address. It's going to be a pointer to F3 at the beginning of your code. That's going to be the initial state of your program counter. The CPU is going to read F3, realize it needs to read 3 more bytes to complete that operation. It's going to complete the operation. Then it's going to increment the program counter to the next operation. So the program counter is a register inside your CPU that says, this is the line I currently need to run. And that's how we go through code, is the program counter just kind of increments. And then at the end of your program, when you return back, it's going to jump the program counter back to the previous program that was running, like your shell or whatever it might be. So that's how the flow of the computer works. There's a register that says, this is the opcode I should be reading. It's going to read that opcode. Hardware is going to do its thing. It's going to advance to the next opcode. And you can spend years of your life building the circuitry to do all of this. But it's all done with just basic gates. So this is the logic of how the computer works. And you'll hear this term program counter a lot. So program counter is what is the current line of code that I'm running. And the other thing to mention here is operation timings. So we saw, when we did this multiplication, we did 5 lines of code here, right? Or sorry, 5 lines of assembly, right? When we did this multiplication, we only did 3 lines of assembly. Which one should we use? Whichever one's faster is definitely the correct answer. The 3 lines seems faster, right? It's just 3 operations on the CPU. But all operations are not made the same. So there is this guy who actually went through and timed how long every single operation took inside of an Intel CPU and published this 400-page PDF of every operation and its timings. And what his results show, because the manufacturers generally don't publish how long each opcode takes, and it's going to be different under different circumstances, is if we look at the add operation, the latency of the add operation is basically 1 cycle. So that means there is it takes 1 computer cycles. So if you're running at a 3 gigahertz computer, you've got 3 billion cycles every second. It takes just one of those cycles to do an add operation. Doing an add with a carry input actually takes 10 cycles. So it takes more cycles if you have an add with carry. Compare operation, 1 cycle. Multiply operation, 10 cycles. So we have that one multiply line is going to take at least 10 cycles to run, compared to add just taking 1 cycle. So that multiply line may take 10 times as long to run, even though it's a single instruction. Something like division, div, 74 cycles minimum running time. So division is really expensive. We're going to want to do all that crazy shift stuff if we can. Because if we have to use the division instruction, we're going to be waiting a lot of cycles to get our answer back. So not all operations are made the same. These are going to vary across different devices. There's ongoing research about how do you optimize this, how do you choose which operation to do. So there's a lot of kind of that goes into this. Yeah? Are these cycles all for inch? So so it depends on how your compiler interprets it, but the div operation is integer division. The fdiv is floating point division. So this is the timing just to do integer division. So yeah, if you do 5 divided by 4.0, you're probably going to have floating point division then. And I'm guessing that's even more cycles. So not all instructions are made the same. They have different timings on how long they take. So hopefully this was useful. I wanted to give you a little bit of insight on how your computer actually takes the code that you've written, you compile it into this object assembly code, and how the object assembly code is not magic, but there's an actual lot of sense on how a program actually runs on your CPU. Because really part of systems is not about building something new, but actually about understanding how the world works so you can improve what already exists and stand on the shoulders of giants. So any questions on this? Yeah.
So when you're talking about like the instructions, how the program counter moves from like instruction to instruction.
Yeah.
Are these, like you said, it was like a memory address, right? Are they like contiguous memory addresses? That's how it gets from one to the other by just having like the value?
Yeah, this program right here would be all of these hexadecimal values are just contiguous bytes of memory. Yeah. There's not going to be any interruptions. So there's 2 really important things that I want to make sure we cover because they're going to be part of the next MP for this class. And the first thing I want to talk about is this idea of Indianness. And it's one of the last things that we need to concern ourselves with about instruction set architectures. And the big idea of Indianness is how do we represent multiple byte characters in memory? So we know that in an integer, inside of C, the size of an integer on every single modern system is 4 bytes. If we run size of int on any one of your computers or any of your cell phones, size of int will return 4. There's pretty much no system that doesn't have 4-byte integers anymore. So that means we have 4 bytes that we need to represent in memory. And I can write a simple program to print out what those bytes in memory are. So here's a program that I wrote that says I'm going to have an integer. I'm going to make this integer exactly equal to the value of 3 in the least significant bit, 2 in the next significant bit, or next significant byte, sorry, 3 in the least significant byte, 2 in the next least significant byte, and 1 in the next least significant byte. So I basically wanted a 2 inside the second byte, 3 inside the third byte. So I did that with a few shift operations. And I could have just written out the number 66,051. But I wanted to make it clear that it's a 1, a 2, and a 3 in memory. And then I'm going to cast a pointer of that integer into a char star, because the nice thing about char stars is everything's 1 byte long. Then I'm going to go ahead and print out those characters as hexadecimal values. So O2x is going to print them out as a hexadecimal. And I am going to, so what do we expect the output of this program to be? Say what? Yeah, I would expect it to be I would expect this to be a whole bunch of zeros, then a 1, then a 2, which is 1, 0, and then a 3. I'd expect this to be the binary output of it, which that would be the hexadecimal 0, hexadecimal 1, hexadecimal 2, hexadecimal 3. That's what I might expect. If I go over to VS Code, I can pull up O4B. That's this exact program. So I'm going to go ahead and gcc o4b.c, run a.out. And oh, that is not what I expected to get. I got O3, O2, O1, O0. So I got 3, 2, 1, 0. Ooh. That is wild. So this is what we call big Indian notation. And this is what the designers of the x86 and x64 systems chose to use. And the idea here is that the least significant bits, least significant byte comes first. So inside each byte, it's still represented as bits in normal order. But the bytes, they choose, if you have a multi-byte thing, they're going to put the least significant byte first, then the next least significant, then the next most least significant, and then the most significant byte last. So the idea of big is that we have to, the last biggest index byte is most significant. So big Indian, the last byte is the most significant byte when you have a multi-byte number. On contrast, little Indian is used by ARM systems. So if any of you guys have an A1 and M1 chip, you can actually run this code, compile it, and when you run this code, you will see 0, 1, 2, 3 as the output. The code is going to be different on those of you who have an M1 chip than those of you guys who have an Intel chip. And little Indian is the least significant byte is last. So when I think of Indianness, think about what the end of the number is. If the end of the number, if it's big Indian, the end of the number is the most significant. If it's little Indian, the end of the number is least significant. And that is what we call Indianness, or the end of a number inside of a system. So this was all fine and good while computers existed on their own. But in modern times, we have to communicate between multiple computers. So we have this idea of a host byte order and a network byte order. So the host byte order is going to be whatever your computer does, whatever your system does. So I don't know what system you have. Some of you guys have told me if you have an M1 chip. I don't know if you're running this code on your cell phone or a Chromebook, which usually has M1 chips on it. But a network byte order is going to be the byte order that we communicate on over the internet. So on the internet, whenever we send data or save a file on things that we might view on the internet, we're going to use network byte order, which is always Little Endian. So network byte order is defined as Little Endian. And there's a C command, a library command, h2n, and that says host to network order. So if you need a number in network order, you should always use h2n, so that way it's always guarantees, no matter what your host is, it will convert that to the network byte order. So there's going to be something coming up in MP2 where you need to do it in network order. So there's going to be one particular number that you have to read in network order, so you're going to have to use h2n, or the opposite, if you know it's in network order, into h, which are library calls to convert a number between host and network order when you're at a byte level. So these two C commands will come in common, or come in handy for you. Yeah?
So let's say the one had 0 bits in front of it instead of 16, so is it the same as the 2? Which one would come first?
So if you, what's the number now?
So like for the one that should be 16 instead of 16.
So here, if we did this, it would have been 2 shift by 8 plus 2, 3 shifted by 8. So the number you actually outputted with now is 3300. You just added to the second register instead, or the second byte instead. So you've added basically 2 and 1 to the second byte. So in just the last minute, I want to talk just very briefly about file types. This is something you almost certainly already know. A file extension is defined as everything after the last dot or period in a file name. So if we look at a file name, we can see where is the last dot in the file name. And the last dot in the file name, .png, we say that this is a PNG file, this is a C file, this is an H file, this is an MP4 file. So we can look at all of the different file types. So there are some file types that are plain text files. These are files that you can read with just normal characters. So a plain text file is any file encoded with human readable characters. And the very last thing is I want to leave you with what you're going to get to start working on in the next MP. And that is, I think it'd be really awesome to really see how some file format works and to understand technical specification. The easiest technical specification I can find is the PNG file format. It is the technical specification of how you save a PNG image. And in MP2, you're going to get to read this file specification, but you don't have to read the whole thing. You just need to read enough to understand how the data is stored inside a PNG file. So you're going to read this actual technical specification that was built by a technical committee, understand how a PNG file format is stored, and then write a program that can actually read through the different chunks that are stored inside this PNG file. And at the very end, you're going to get to hide something inside a PNG file. So I've already hidden an image inside our 240 logo just for you to find out what I hid inside of that. So by this end of the MP, you're going to find what I've hidden for you inside this 240 image. So I'll be here after lecture for a few minutes. MP2 will be up tonight. Remember, MP1 is due tomorrow night by midnight. Have an amazing weekend, and I will see you back here on Tuesday, where we'll begin talking about memory and how we actually store all of this data inside of RAM. So I'll see you guys on Tuesday.